Okay, this is part 2 of the design example of a buck converter and the simulation verification. In part 1 we went through a complete design example for a given specification, and we also developed the schematic of the Plex simulation and went through the various settings and components. And in part 2 we will look at the various current, voltage and signal waveforms, mostly in steady state, but we'll also look at some of the startup transient waveforms. First we'll look at the output voltage waveform. So click on this oscilloscope that is connected to the output voltage. Okay, so this is the output voltage, and as I said, this corresponds to several hundreds of switching periods. So let's here is the startup transient that I said we'll be interested in looking, but we will come back to this later, or we go through this steady state waveform verification first. So let's look at somewhere towards the end after it has reached completely steady state. So I can zoom in on just the last few cycles, probably somewhere here. Okay, and so this is the output voltage, and we expect this to be 12 volts constant, and you can see it is exactly 12 volts. If I zoom in further, right at the 12 volts magnitude point, so this is the actual output voltage, and if you look at the peak to peak variation, this looks more like a triangular waveform. The reason is the ripple is dominated completely by the ESR component, and the ESR component has the same wave shape as the inductor current, which is triangular. So if you recall, we designed for a peak-to-peak ripple of 60 millivolts, and each division is 50 millivolts, as you can see from here, and so this is exactly equal to 60 millivolts, and that sort of verifies our design is correct. Okay, now that we have verified the buck converter operates correctly, results in the correct output voltage, let's go ahead and look at the detailed switching level waveforms. So we'll begin with the waveforms corresponding to this PWM process by looking at what is inside this probe, which was just nothing but the relational operator. Let's look at that again. So it has the relational operator, and we're looking at both the two inputs as well as the single output. So what comes out is really a vector of 3 signals. So let's look at the this output. So once again, with these thousands of switching periods, we're not able to make out anything. So let's focus only on the last few cycles. So let's select about 3 of the last switching periods. So again, this is the PWM process. So the green signal here is 0.4 volts, and that corresponds to the control signal. The red waveform is the sawtooth. It goes from 0 to 1 with a switching period of 2.5 microsecond. And the PWM process is whenever the control signal, the green, is higher than the red, that is from the start till this point, the output of PWM block is 1, as shown here by the blue waveform. And when the red is higher than the control signal, then your output is 0. So once again, at the start of the next cycle, when the ramp goes to 0 and the control signal is higher than that, the PWM output is 1. And once the ramp has reached the level of control signal, the output comes to 0, and so on. Okay, then we will look at the V sub A waveform, which is the switching signal applied to the output LC filter, which essentially this voltmeter. So again, let me zoom in on the last few periods, probably here. Okay. So again, it's kind of hard to make out. Let me just change the background to black. Let's see if that makes it better. Okay. So this is the V sub A waveform, and the scales are 0 here, and this peak point is 30 volts. So during the on interval, when the switch is on, the output, the V sub A is 30 volts, and when the switch is off, it is 0. So switches between 0 and 30, because both the MOSFET and the diode are ideal. This is exactly switching between 0 and 30. If not, this level would be a negative of the diode drop, and this level will be Vn minus a small drop across the MOSFET. But for the ideal case, it is 0 to 30. and it is the average of this waveform that is equal to the output of 12 volts. Okay, next in this probe, if I click into it, what I have is the inductor, and I'm measuring the inductor current as well as inductor voltage in this probe part. So let's look at these two waveforms. Okay, so the inductor current and voltage waveforms are shown here, and this is a nice feature of Plex, where here this area shows the complete waveform, and I can zoom in. For example, if you want to zoom in right at the end to show the steady state waveforms, it just highlights which region is being zoomed, and this shows the zoomed region. Okay. So let's close this for the time being. Let's look at the actual inductor waveforms. So the red waveform is the inductor voltage waveform. So as we would expect, it switches between, during the on interval, which is this interval, switches between V and minus VO, so which is 30 volts minus 12 volts, which is 18, and this is exactly 18 volts. And during the off interval, it should be negative of VO, so it's minus 12 volts as confirmed here. Now this also verifies our small ripple approximation. So we were able to draw the ideal waveform where this was just a straight line of value equal to V minus VO, and that is kind of confirmed by this being a straight line at 18 volts. If the output ripple was really high, then you would have a very large variation during this on interval as well as during the off interval. Looking at the inductor current waveform, so that is the green waveform. Let me zoom in only this part. So this is switching between roughly just below 4.5 to about 5.5. So that is the peak-to-peak variation of 1 ampere. That's exactly what we designed. Our delta IL by design was 1 ampere. And also notice that our worst case for inductor was the minimum duty ratio, or the maximum input voltage, which is exactly what we are doing the simulation for right now. So this does correspond to the worst case, and our worst case value of peak-to-peak inductor current ripple is exactly what we designed for, of 1 ampere. Okay. This is also a good set of waveforms to look at the initial startup transients. So let me zoom in somewhere near the startup period. So once again, remember, these are the inductor voltage and current waveforms. If you look at the very beginning, right at the start. Okay. So let's look at the inductor voltage waveform. During the on interval, it is almost exactly equal to 30 volts, because VO is just starting from 0. So this voltage should be V in minus VO. So there is just 30 minus 0, 30 volts. In response, the inductor current rises faster than its steady state rate. During the off interval, the voltage should be minus VO, and since VO is just 0, this voltage is also 0. And in response, the inductor current does not change at all, because the voltage across the inductor is 0, therefore the change in the current is 0. And in the next cycle, it starts from this initial value and rises at a slope again much higher than its steady state rate, because the voltage is still roughly equal to 30 volts, because the output voltage is only rising slowly. And so clearly the inductor current keeps rising from one cycle to the next cycle, and that is the startup transient. And the output and the inductor voltage has a similar wave shape. Now if you keep going in this way, we're just progressing, you can clearly see the inductor current rising from one period, keeps rising. So let me just zoom in some greater portion of the startup period. So let's look at so much of the. So clearly the inductor current has now reached much higher than the steady state value of 5 amperes. That is because of the LC resonance. And the output voltage is also building up, even though it is not shown here. It can be inferred. Actually, the magnitude of the off state voltage is simply VO. It is minus VO, but its magnitude is equal to VO, and you can see it is clearly rising, and it is reaching towards it's going towards minus 12, or VO of plus 12. So if you look at here, so after these LC oscillations, eventually it is tending to go to the steady state. Notice that in between it has also gone into DCM mode. So you can see the inductor current was rising during the on interval, falling during the off interval, and for a small period it remains zero. It is neither rising or falling, and that corresponds to the DCM mode of operation. Next, let's look at some more steady state switching waveforms. So this time we'll look at the various current waveforms. So this scope monitors the inductor current IL, the capacitor current IC, as well as the input current IN. So let's look at these three waveforms. Okay, so the top waveform is the actual inductor current, the middle waveform is the capacitor current, and the final one is the input current. So I could even name them. So plot 1, I will call it as the IL. And the plot 2 is plot 2 is I sub C, and plot 3 is IN. Okay. So once again, let's look at just the final few switching periods. Maybe zoom in even further, and let's make it the magnitude also zoomed in. Zoom in here, and same thing for here as well. So the inductor current we've already seen, so not much to explain. It is the average value of 5 amperes, and the peak-to-peak ripple is exactly 1 ampere as we designed. So let's focus more on the capacitor current. So what do we expect the capacitor current to be? So it should have the same exact wave shape as the inductor current, except for the DC component of IL. So the IL minus its average value of IO, that is minus 5 amperes, should be exactly equal to IC, and that is clearly what we see here. It switches, it varies between minus 0.5 to plus 0.5 for a peak-to-peak variation of 1 amperes, and the average by definition of steady state should be 0, and it is exactly equal to 0 as confirmed by the middle waveform. Finally, the input current, it is exactly same as the inductor current when the switch is on. So that is during the on interval, it does go from about 4.5 to 5.5 amperes, and during the off interval, it is a diode which conducts and the switch is off. Therefore, the input current is 0 during the off interval, and the average value of this should be exactly equal to D times the load current of 5 amperes. So it's 0.4 times 5. Finally, I also want to show the ripple voltage in the output capacitor. Now, in a real capacitor, we cannot distinguish between the ripple component of just the ideal capacitor part and the ripple component of the ESR separately, because the ESR is a distributed component, so we cannot separate it out. But in simulation, we can do that. In fact, we model the ESR as an external capacitor, so we can separately monitor the voltage across the ideal capacitor and that across the ESR and across the total capacitor. So what I've done is I've added another voltmeter across just the ideal capacitor, and I'm going to compare that with the total voltage in the same scope. So notice that I have now a multiplexer which multiplexes two signals. One is the total output voltage including the ESR component, and the other one is just the ideal capacitor voltage waveform. So let's monitor this voltage waveform. And in order to do that, we still need to run the simulation because I've added a new part now. Okay. So here are the two voltage waveforms. One is the final output voltage, other is the voltage across the ideal component of the capacitor. And the two, as we would expect, are very close to each other. They only differ by the ESR component, both during the transient as well as during the steady state. So our interest is really in the steady state to compare the ripple components. So let's zoom in near the steady state period and really zoom in on the magnitudes. So clearly it has probably not reached complete steady state. We may have to run several more cycles to make it really flat. But the scales are, as you can clearly see, they are very highly magnified. Anyway, the point was the output voltage ripple is 60 millivolts, as we can confirm from here, and that is entirely due to the ESR drop, whereas the ideal capacitor component has almost no ripple, and that's exactly what our assumptions were, that the compared to the ESR ripple, the ripple due to the capacitive component is negligible, and that is kind of confirmed by these waveforms. Okay, then let's look at the simulation under a different operating condition. So for example, we can change the input voltage. It's presently the maximum of 30 volts. Let's change it to the minimum input voltage condition, and that is 20 volts. So change the input to 20, and we will simulate the converter under the same full load condition. So the load is the same, 2.4 ohms. But since we change the input to 20 volts and we still want the output to be 12 volts, we need to change the duty ratio. In a closed loop simulation, this will happen automatically. All we need to do is change the input voltage, either a change or a change as a step, and the controller will automatically change the duty ratio to regulate the output voltage. But since we are doing just open loop simulation, let's manually change this to corresponding value. That's 12 over 20, that is 0.6 is the new duty ratio. And let's run the simulation, and we look at some of the waveforms again corresponding to this set of operating condition. So simulation start, and it has already run. So the first waveform we will look at is the final output voltage, just to confirm that everything is working properly. So just click on the output probe. So clearly we can see that the output is still regulated at 12 volts. I can zoom in near the end. So after the transients have died down, the output voltage is regulated to very close to 12 volts. The reason why it is not exactly 12 volts is we have included the series resistance of the output inductor, and that has a very small drop. So this is about 11.97 instead of exactly 12 volts. The next waveform we can look at is the this V sub A waveform. So let's click on this scope. And again, let's zoom in only towards the steady state region, and now the V sub A switches between 20 volts and 0 volts, and it is average is still the output voltage of 12 volts. And finally, let's also look at the inductor current waveform, and I think that is available as part of this probe. So let's look at this one. So we are seeing both the inductor voltage as well as the inductor current, and again zoom in here near the end. So the inductor voltage is switching between Vn minus Vo, so that would be Vn of 20 minus Vo of 12, so that is the positive 8 volts here. And during the off interval it should be minus Vo as before, and that is minus 12 volts. And we can also notice that the duty ratio has increased from 0.4 to 0.6 because the on interval is higher than the off interval. So then finally let's look at the inductor current. Let's zoom in on the inductor current. Let's just look at the last 3 periods, and again clearly the load current average value is 5 amperes, and the peak to peak ripple is slightly less than before, as we would expect, because the delta I of 1 ampere that we designed for corresponds to the worst case condition, which was the maximum input voltage. Now when we simulate for a lower input voltage, then we expect the delta I to be smaller, so it is going from 4.6 up to about 5.2, so it's only about 0.6 amperes instead of 1 ampere as we would expect. Okay, then I also wanted to show a simulation corresponding to a slightly different design. So we are going to use a different design of the output capacitor. If you recall, I mentioned that for the output capacitor we could use the either a film capacitor or MLCC, which is a multi-layered ceramic capacitor, and both of these have almost negligible ESR, and so therefore we could use low value capacitance and still meet the delta Vo ripple specification. So let's do a simulation and see how that performs. So if you recall, I think the requirement on just the capacitive impedance, ripple based on just the capacitive impedance, I think we require a capacitance of more than 5 or 6 microfarad. So let me use a film capacitance or multi-layer ceramic of say 10 microfarads. That's 10e minus 6, and the ESR is negligible. So let's say instead of 60 milliohms I would use say 1 milliohm, so it's 0.001. Okay, so let me also simulate this corresponding to the worst case condition, which we know is the maximum input voltage. So let's go back and change the input to 30 volts instead of the 20. And again, we know that in open loop simulation, if we change the input voltage to get the same output, we need to change manually the duty ratio as well. So let us change it back to the 0.4. So now we are ready to simulate corresponding to a different capacitor design. But it turns out that in order to get the output voltage ripple waveform accurately, we need to change the simulation parameters. So the default value for the maximum step size had been this 1 e to the minus 5, and our switching frequency is 2.5 microseconds. So let's change it to a much smaller value. Let's say it's 1 e to the minus 7. So what this means is it will take step sizes no larger than this 0.1 microsecond, which is good enough for simulating time periods which are 2.5 microsecond. So let's do that, and simulation start. So even with the much smaller time steps, we can see that the simulation did not take any time at all. It's already completed. So with this changed output capacitor, the thing that is really changing are the output voltage and its ripple wave shape as well as the magnitude. So let's look at the output voltage in this scope. The first thing that you can immediately notice is because of the significantly lower value of capacitance. So we went from 200 microfarad to 10 microfarad. So therefore the resonant frequency, which is the 1 over 2 pi square root LC, so that has increased, and also the damping to that resonance is significantly increased. So the oscillations die down within a few resonant cycles, and we reach steady state somewhere here within about 0.3. So this is 0.3 millisecond, within 0.3 millisecond. So anyway, what we are really more interested in observing was the output voltage ripple. So let's zoom in on the output voltage, and let's look at the last few switching periods. Okay, so clearly the wave shape is very different from what we saw in the previous simulation with larger capacitance and larger ESR. There the ripple was dominated by the ESR voltage component, and therefore it had the same wave shape as the capacitor current, which is same as the AC component of the inductor current. So it's a triangular wave shape. Whereas here the ripple is dominated more by the capacitive impedance, because the ESR contributes only, it's 1 milliohm times peak to peak current of 1 ampere. It only gives the peak to peak ripple of 1 millivolt. Whereas the capacitive impedance contributes, as we can see from here, it's about say 11.96 to about 11.99, about 30 millivolts, and just 1 millivolt of that is due to the ESR component. So once again, this is the integral of the capacitor current, and therefore it is closer to this sinusoidal or a parabolic waveform. This is the integral of the triangular waveform, which is the current. So this is exactly what we expected for a low capacitance and negligible ESR design. Most of the other waveforms, like the inductor voltage or the inductor current, this vis-a-vis, they would remain exactly the same, corresponding to the previous larger capacitance design. So we don't need to look at them again. Okay, so we have looked at several steady state waveforms of various voltage and currents, as well as these PWM signals and so on, both during steady state and during the startup transient. Now in the next video, actually part 3 of this buck example and simulation, we will look at how to get the cycle by cycle average of these various quantities, and also compare the switching level waveforms, their averaged waveform, as well as the waveforms obtained from a complete ideal transformer based average model.